In mathematics and computer science, the floor and ceiling functions map a real number to the largest previous or the smallest following integer, respectively. More precisely, floor, x, equals is the largest integer not greater than x, and ceiling, x, equals is the smallest integer not less than x. Notation: Carl Friedrich Gauss introduced the square bracket notation for the floor function in his third proof of quadratic reciprocity. This remained the standard in mathematics until Kenneth E. Iverson introduced the names floor and ceiling, and the corresponding notations, and in his 1962 book A Programming Language. Both notations are now used in mathematics. This article follows Iverson. The floor function is also called the greatest integer or interior function, and its value at x is called the integral part or integer part of x. For negative values of x, the latter terms are sometimes instead taken to be the value of the ceiling function, that is, the value of x rounded to an integer towards 0. The language APL uses AOESHX. Other computer languages commonly use notations like interior, x, int, x, or floor, x, C, C++, R, and Python. In mathematics, it can also be written with boldface or double brackets. The ceiling function is usually denoted by ceil, x, or ceiling, x, in non-APL computer languages that have a notation for this function. The J programming language, a follow-on to APL that is designed to use standard keyboard symbols, uses for ceiling and for floor. In mathematics, there is another notation with reversed boldface or double brackets, or just using normal reversed brackets x. The fractional part sawtooth function, denoted by for real x, is defined by the formula for all x. Examples: typesetting. The floor and ceiling function are usually typeset with left and right square brackets where the upper or lower horizontal bars are missing, and, for example, in the LaTeX typesetting system these symbols can be specified with the \lfloor, \rfloor, \lceil and \rceil commands in math mode. HTML 4.0 uses the same names, and lfloor, and rfloor, and lceil, and rceil. Unicode contains code points for these symbols at U+2308 to U+230B, or XOR per mil, alias XOR. Definition and properties: in the following formulas, x and y are real numbers, k, m, and n are integers, and is the set of integers. Floor and ceiling may be defined by the set equations. Since there is exactly one integer in a half-open interval of length 1, for any real x there are unique integers m and n satisfying. Theta and a may also be taken as the definition of floor and ceiling. Equivalences: these formulas can be used to simplify expressions involving floors and ceilings. In the language of order theory, the floor function is a residuated mapping, that is, part of a Gauss connection. It is the upper adjoint of the function that embeds the integers into the reals. These formulas show how adding integers to the arguments affect the functions. The above are not necessarily true if n is not an integer. However, relations among the functions, it is clear from the definitions that, are with equality if and only if x is an integer, that is. In fact, since for integers n, negating the argument switches floor and ceiling and changes the sign, and negating the argument complements the fractional part. The floor, ceiling, and fractional part functions are idempotent. The result of nested floor or ceiling functions is the innermost function. For fixed y, x mod y is idempotent. Also, from the definitions: quotients, if m and n are integers and n a per mil 0. If n is positive. If m is positive. For m equals 2, these imply. More generally, for positive m. The following can be used to convert floors to ceilings and vice versa. If m and n are positive and k', then, since the right-hand side is symmetrical in m and n, this implies that. More generally, if m and n are positive. This is sometimes called a reciprocity law. Nested divisions: for positive integers m, n, and arbitrary real number x. Continuity. None of the functions discussed in this article are continuous, but all are piecewise linear. A and are piecewise constant functions, with discontinuities at the integers. Also has discontinuities at the integers, and as a function of x for fixed y is discontinuous at multiples of y. A is upper semi-continuous and AA and A are lower semi-continuous. X mod y is lower semi-continuous for positive y and upper semi-continuous for negative y. Series expansions. Since none of the functions discussed in this article are continuous, none of them have a power series expansion. Since floor and ceiling are not periodic, they do not have uniformly convergent Fourier series expansions. X mod y for fixed y has the Fourier series expansion. In particular, x equals x mod 1 is given by. At points of discontinuity, a Fourier series converges to a value that is the average of its limits on the left and the right, unlike the floor, ceiling and fractional part functions. For y fixed and x a multiple of y, the Fourier series given converges to y/2, rather than to za mod a equals a0. At points of continuity, the series converges to the true value. Using the formula x equals xa floor, x equals xax gives. Applications. Mod operator. The mod operator, denoted by x mod y for real x and y, ya permel 0, can be defined by the formula. X mod y is always between 0 and y. That is, if y is positive. And if y is negative. If x is an integer and y is a positive integer. X mod y for a fixed y is a sawtooth function. Quadratic reciprocity. Gauss's third proof of quadratic reciprocity, as modified by Eisenstein, has two basic steps. Let p and q be distinct positive odd prime numbers, and let. First, Gauss's lemma is used to show that the Legendre's symbols are given by and. The second step is to use a geometric argument to show that. Combining these formulas gives quadratic reciprocity in the form. There are formulas that use floor to express the quadratic character of small numbers mod odd primes p. Rounding. For an arbitrary real number, rounding to the nearest integer with tie breaking towards negative infinity is given by truncation. The truncation of a non-negative number is given by the truncation of a non-positive number is given by. The truncation of any real number can be given by, where SGN, x, is the sign function. Number of digits. The number of digits in base b of a positive integer k is. With the right side of the equation also holding true for factors of factorials, let n be a positive integer and p a positive prime number. The exponent of the highest power of p that divides n is given by the formula. Where is the way of writing n in base p? Note that this is a finite sum, since the floors are 0 when pkn. Beatty sequence. The Beatty sequence shows how every positive irrational number gives rise to a partition of the natural numbers into two sequences via the floor function. Euler's constant. There are formulas for Euler's constant I cubed equals 0.5772156649. That involve the floor and ceiling, for example. And Riemann function. The fractional part function also shows up in integral representations of the Riemann zeta function. It is straightforward to prove that if I, x, is any function with a continuous derivative in the closed interval, a, b, letting I, n, equals null s for real part of s greater than 1 and letting a and b be integers, and letting b approach infinity gives. This formula is valid for all s with real part greater than a 1. And combined with the Fourier expansion for x can be used to extend the zeta function to the entire complex plane and to prove its functional equation. For s equals I florin plus it in the critical strip. In 1947 van der Pol used this representation to construct an analog computer for finding roots of the zeta function. Formulas for prime numbers. N is a prime if and only if. Let a greater than 1 be an integer, Pn be the nth prime. And define. Then, there is a number I equals 1.3064. With the property that are all prime. There is also a number I per mel equals 1.92878800. With the property that a rule prime I euro x is the number of primes less than or equal to x. It is a straightforward deduction from Wilson's theorem that also, if Na per mel 2 yen. None of the formulas in this section is of any practical use. Solved problem. Ramanujan submitted this problem to the Journal of the Indian Mathematical Society. If n is a positive integer, prove that unsolved problem. The study of Waring's problem has led to an unsolved problem. Are there any positive integers ka per mil 6 yen, such that Mahler has proved there can only be a finite number of such k. None are known. Computer implementations. Many programming languages provide standard functions for floor and ceiling. Spreadsheet software. Most spreadsheet programs support some form of a ceiling function. Although the details differ between programs, most implementations support a second parameter a multiple of which the given number is to be rounded to. For example, ceiling 2, 3, rounds to up to the nearest multiple of 3, giving 3. The definition of what round up means, however, differs from program to program. Until Excel 2010, Microsoft Excel ceiling function was incorrect for negative arguments. Ceiling, -4.5 was -5. This has followed through to the Office OpenXML file format. The correct ceiling function can be implemented using int value. Excel 2010 now follows the standard definition. The Open Document file format, as used by OpenOffice.org and others, follows the mathematical definition of ceiling for its ceiling function, with an optional parameter for Excel compatibility. For example, ceiling, -4.5 returns a 4. See also, nearest integer function, step function, notes. References, J.W.S. Castles, An Introduction to Diophantine Approximation, Cambridge Tracts in Mathematics and Mathematical Physics 45, Cambridge University Presser, Crandall, Richard. Pomerantz, Carl, Prime Numbers, A Computational Perspective, New York, Springer, ISBN A0-387-94777-9, Graham, Ronald L. Knuth, Donald E. Patashnik, Oren, Concrete Mathematics, Reading Ma Addison Wesley, ISBN A0-201-55802-5, Hardy, G.H. Wright, E.M., An Introduction to the Theory of Numbers, Oxford, Oxford University Press, ISBN A978-0-19-853171-5, Nicholas J. Hyam, Handbook of Writing for the Mathematical Sciences, Siam ISBN 0-89871-420-6, PA25, ISO-IEC. ISO-IEC 9899-1999, E, Programming Languages C, 1999. Section 6.3.1.4, PA43. Iverson, Kenneth E., A Programming Language, Willier, Le Mermier, France, Reciprocity Laws, From Euler to Eisenstein, Berlin, Springer, ISBN A3-540-66957-4, Ramanujan, Srinivasa, Collected Papers, Providence RI, AMS/Chelsea, ISBN A978-0-8218-2076-6, Riebenboim, Paulo, The New Book of Prime Number Records, New York, Springer, ISBN A0-387-94457-5, Michael Sullivan. Pre-Calculus, 8th edition, PA 86, Titchmarsh, Edward Charles. Heath Brown, David Rodney, The Theory of the Riemann Zeta Function, Oxford, Oxford UP, ISBN A0-19-853369-1, External links, Haswinkel, Michiel, ed., Floor Function, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Angstrom Tefan Forupska 1/2, Integer Rounding Functions, Interactive Information Portal for Algorithmic Mathematics, Institute of Computer Science of the Czech Academy of Sciences, Prague, Czech Republic, retrieved October 24, 2008, Weierstein, Eric. W. Floor Function, MathWorld. Weierstein, Eric W., Ceiling Function, MathWorld.